I'm Andrew Johnson, and this is my Lab 3 Black Holes and Orbits for Physics 2211. In this experiment, there were two parts. Part 1's goal was to find the mass of a black hole based on a given star's motion, and the part 2 was to determine what initial velocity the spaceship needs in order to orbit both a planet and a moon without crashing into each other. A preview of the results were that the mass of the black hole was 3.7 times 10 to the 37th kilograms, and the initial velocity of the ship was 10,000 to 21,964 in 0 meters per second. There are two fundamental physical principles that are key to understanding this lab. First is Newton's second law with the position update formula, the velocity update formula, and that the force can be split into both the perpendicular and parallel components. Also, universal gravitation constant was necessary, where force is equal to the universal gravitation constant times the mass 1 times the mass 2, all over the distance between the two masses squared. In part 1, the system was the black hole, and the surrounding was the star and everything else in the universe. In this case, the star really was the only thing else in the universe other than the black hole, because this simulation only considered the star's effect on the black hole. The initial conditions given were that the mass of star was 2 times 10 to the 30th kilograms. The code in part 1 included a while loop where the velocity was updated, the momentum was updated, and calculated dp/dt, which is the change in momentum over the change in time, which that was also equal to the net force. This could then be split up into the parallel and perpendicular components, where the parallel component was calculated by p hat times the magnitude of the change in momentum, and the perpendicular component was just the dp/dt minus the parallel component. The mass of the black hole can then be found using a formula where you manipulate the gravitational, the law of gravitational, the universal gravitational law, where you can find the mass of the black hole by simple algebra. Also, arrows were used to visualize the effect that the black hole had on the star, given by the code on the right. The results from part 1 was that the mass of the black hole was 3.7 times 10 to the negative 37th kilograms. This was given by running a simulation by different time steps and taking the average using Excel of all of the masses found by the while loop. In part 2, the system was given to be the spaceship, and the surroundings were the black hole, planet, and again everything else. But everything else really doesn't matter because the black hole and planet were the only two objects that force was considered to act on the spaceship. The initial positions are given as follows, where the planet started at the vector 0, 0, 0, and the moon started at 9 times 10 to the 8th, 0, 0. The ship would start at negative the moon's position, so negative 9 e to the 8th, 0, 0. And down here you can see the constants given, or the gravitational constant, the planet's mass, the moon's mass, the ship mass, and delta t was also given before the simulation was run. The code for part 2 was first that we had to calculate the distance between the moon and the planet, which was given our planet to the moon. Also the force, where we used the universal gravitational law. Also the ship to the moon, the position of the ship to the moon, and the force that the moon had on the ship. And then the Fnet was calculated by adding the planet on moon and ship on moon forces. Also, the planet to the ship was calculated and the moon to the ship was calculated. Their forces were added together to get the Fnet on ship. So really, you're considering what effect the ship has on the moon, also what the moon has on the ship. The results for part 2 were given that initial velocity of 10,000, 21,964 0 meters per second works, and it doesn't collide into the ship. As you can see on the right, the spacecraft goes around and around and around and oscillates in this motion without colliding into the moon or the star at all. Throughout this experiment, there are a few potential errors that could skew the results. First was that there may have been computational errors, where there were errors in mathematical equations, or the time steps were too large to accurately account for a continuous gravitational effect. Also, that guessing the initial velocity in the spaceship for part 2 could be an error because there was no mathematical way in guessing. It was just pretty much a plug and chug and see what works. For the first what does it mean in part 1, it asks how are the net forces in parallel and perpendicular components different from the rate of change of momentum in its parallel and perpendicular components. Well, mathematically, Fnet and dp/dt are the same vector as seen as calculated in the code. However, in interpreting their components, the net force is viewed as the cause, where dp/dt is just the effect of the force. The parallel component affects the speed, magnitude, and momentum, where the perpendicular component affects the direction and angular momentum. The second what if for part 2 is if this imaginary system has a black hole, a star, a planet, and a moon. If we wanted to predict the motion of the entire system, what would we need to include in our computational model? And would there be any dominant interactions, or would they all contribute more or less equally? Well, if there were a black hole, a star, a planet, and a moon, we would have to computationally see how all of them affect one another. And there would be a dominant contribution because a black hole has way more mass than a star, a planet, and a moon, and a star has way more mass than a planet and a moon. So we'd have to consider the dominant effect of the black hole and star on the others compared to the planet and the moon that might not have as much of an effect on the star and a black hole because they're so much more massive. Thank you for watching, and I hope you have a great day.